Does enthalpy just relate with being in a liquid?
No,
Or,
it's like any state function, it's dependent on the states, solid, liquid, gas, aqueous, whatever. So that's why, and that's a very important question to ask, but that's why in the table, they give different values for enthalpy, free energy. Well, you guys will use free energy. So enthalpy. For even the same substance for different states, like H2O solid versus liquid versus gas.
okay,
You have different values for enthalpy of formation of those substances. So you have to pay attention to the states when you're doing calculations like what we're about to do. Roll. Was not here, Bass is not here. Bishop here. Brad, Audio. Chestnut, Colwood, Robinson, Gerard, Green, Kennedy, Leonard. The Hammond board is here. Spall, Sullivan is here. Swissack, and we just want Robinson.
brag.
Right. Okay, so last time we were here, we were discussing Hess's law, and I think it's important that I recap Hess's law so that you can understand how to do the example we're about to do. So let me a word. So if you remember, I said that if you have a reaction that can go from A to C, and now the enthalpy of that reaction is delta H3, but you can also go from A to B, which is an intermediate, and then to C. So for here, delta H1 would be the enthalpy change for going from A to B, and delta H2 would be the enthalpy for the reaction going from B to C. So what I was saying was that according to Hess's law, delta H3 would be equal to delta H1 plus delta H2, right? So because what Hess's law says is that independent of how you get from A to B, the enthalpy change overall will be the same, all right? It doesn't matter if you go through one step or more than one step, all right? So another way I recall showing you how this works is that if you write down A going to B, and delta H1 again is the enthalpy change for that reaction, and then B going to C, and delta H2 is the enthalpy change for that reaction. Then when you add these, you're going to be able to add those two. So therefore, when you add these will cancel out. So going from A to C would be delta H1 plus delta H2, which again would be equal to delta H3, right? So this is the principle that we're going to employ in solving problems such as the problem that we're going to do right now. And I'm going to need some space. So again, I'm going to copy, paste this into Word.
Because you're on the draw page of your document.
What's that?
Is it because you're on the draw page of your document,
What do you mean? Oh, you mean if I do this?
like the text page?
But this, the page thing is not highlighted here. Ah. You know what, let me, see if I can work with this here, but if I bring this up. Wrong. Um. This right here, it's not highlighted. So I can't even. Oh, okay. I understand where I didn't go through all that, but anyway. Okay, so basically, what the question is asking is for you to calculate the enthalpy change of the first equation. All right. So this is delta H, that should be delta not D. For this equation here, using the enthalpy changes for these equations, these three equations given after that. So this is how I would go about doing this. The first thing I would do is I would compare each equation, each of the three equations below with the equation of which you're trying to find the delta H, right? So the first one I notice is that in equation B, you have carbon on the left side here, which is true for the first equation. However, there's a coefficient of 2 here, right? So what I would do to this equation here is that because there's a coefficient of 2 here, I would multiply that equation, that entire equation by 2. So when I do that, I'm going to end up with 2 times carbon solid plus 2 O2 gas to give 2 CO gas. All right. And the result of the change in the delta H would be that delta H for this new equation would be 2 times minus 393.5 kilojoules. All right. So that's
DO gas or is it CO2?
CO2, thank you, CO2 gas, all right? Okay, so that's the first thing, right? Because you have a 2 here, beside the graphite, you'd multiply this equation by 2 so that you have a 2 here beside the carbon as well. Okay, the next thing I'll do is compare equation C to equation A. And when you compare equation C to equation A, you'll notice that you have C2H4 on the left, whereas in the first equation it's on the right. So what I would do is switch the reactants and products so as to get the C2H4 on the right in the case of equation C. So I'm just going to write here switch. And that means that the resulting switch would be 2 CO2 gas plus 2 H2O liquid to give C2H4 gas plus 3 O2 gas. And delta H for that, when you switch it, what happens to delta H? Anybody can tell me?
They go positive.
It becomes positive because it was negative before, all right? So this becomes delta H equals to 1410.9 kilojoules, all right? And then now we get to the last equation here. Again, we're comparing this equation to the first one, and we notice that we have 2H2 on the left side here in the first equation. Here we have only 1, so what I would do to this, in order to get a coefficient of 2 here, is that I multiply by 2. So in that case, you're going to get 2H2 gas plus 2 times half O2 gas to give 2H2O liquid. And delta H for that would be what? What would delta H for that equation be?
285 times 2.
Exactly, 2 times minus 285.8 kilojoules. All right, so after doing that, when you add up all these equations here, of course, we all know what happens. You cancel out those items that are common to both sides. So in this case, that would mean that these two H2Os would cancel out with these two H2Os. These two carbon dioxides will cancel out as well. And this one is not immediately obvious, but you'll notice that you have 2 oxygens here plus 1. So that's 3 oxygens total on the left side. And those will cancel out with those 3 oxygens on the right side. So the only thing that would remain would be 2 carbon plus 2 H2 gas to give C2H4 gas, and therefore the delta H of this equation here, oh, by the way, this equation here will be basically the same thing as this equation here, which means that the delta H value that we're going to get here would be the sum of all these delta H values that we have on the right of that setup. So what I'm going to do now is calculate what this is equal to and what this is equal to, and then add them up. So 393.5 minus times 2, so that gives minus 787.0 kilojoules. And then down here would be minus 285.8 times 2, and that would give minus 571.6 kilojoules. And then now we add up everything to get the final delta H. So let's see here. 787.0 minus sign plus 1410.9 minus 571.6. And according to my calculations, and please correct me if I'm wrong, but the answer I got is 52.3 kilojoules. And that's how you determine the enthalpy of that equation based on the values given for the other equations. All right, so that's it. Any questions?
Are there any more rules other than just switching the signs for?
Well, when you switch reactants and products, the sign changes, and whatever you multiply the entire equation by, you multiply the delta H value by the same number. Those are basically the 2 types of modification that you would have to employ when it comes to solving problems like these. Now, the key thing is, of course, knowing how to manipulate the other equations so that when you add them up, you get the equation for which you're trying to find delta H. Right, that's the key thing. And the way you do that is that you compare each of the equations for which the delta H values are given. You compare each of them to the initial equation that you're trying to find delta H, right? So like in this case here, when I compare equation B to equation A, I notice that you have two as a coefficient in front of the carbon here, but only one here. So what that tells me is that I need to multiply this entire equation here by 2. All right? In this case here, I notice that the C2H4 is on the left, whereas in the first equation, it's on the right. So that means I have to switch it. Now, there are some cases, and I'm not sure if that's one of the cases in the assignment, but there are some cases where you have to do a combination of multiplying and switching. Right? In which case you have to change the sign and multiply right through by the appropriate number. So it all depends on, you know, the type of question you're given. In fact, let me see what the assignment has to offer. No, that one. Okay, so. Okay, so number 9. It says calculate delta H for this equation, so they gave you the equation here, and they gave you the different equations related with your corresponding delta H values. Okay, so, all right, so as I said before, what you do is compare each of these equations to the first one, right? So let's start off by looking at the ammonia. We have 4 ammonias here, right? In fact, this is an example of what I just mentioned. You have 4 ammonias here, right, on the left. But here you have 2 ammonias on the right. So what do you think you need to do to this equation? Let me turn on my pen.
You multiply by 2 and flip it.
Exactly. So in this case here, you're going to multiply by 2 and flip. Right? So basically, when you do that, you're going to end up with 4NH3, yes. And by the way, please remember to include the state symbols because that can make a difference. What was I saying? 4NH3 and then 2N2 gas and then 6H2 gas, right? Which means what happens to the delta H for this?
Flip and double,
You flip and double, which means that what happens to the sign?
it'd be positive.
Right, so therefore it's 2 times 91.8 kilojoules, right? Because when you flip it, the sign changes, and when you double everything, the value is doubled as well. Okay. Okay, what about so here's another thing now. You'll notice that there are 5 O2s here. But the thing is that you have O2s in different equations given down here, right? So I would not worry about the O2 quite yet, right? It will all work out eventually, right? So what I would do is move on to the NO, right? So, because we have 4 NOs here, what do you think you need to do to this equation? Because this equation has NO here on the right, and there are 2 of them, and we have 4 NO on the right here. So what do you think you need to do to this equation? Multiply by 2. So you're going to end up with 2N2 gas plus 2O2 gas to give 2NO. I'm sorry, 4NO gas. And delta H for that is what?
2 times negative 1.
Exactly, 2 times minus 180.5 kilojoules. Very good. Okay, and then now we come to the third equation. We're going to compare the third equation to this equation here. So we notice that what they have in common is water, right? But in this case here, we have 2 water molecules. In this case here, we have 6. So what do you think we need to do to this equation?
Multiply by 3.
Multiply by?
3.
3, exactly. So you're going to end up with 6H2 gas plus 3O2 gas to give 6 H2O gas, right? And delta H for that would be equal to what?
3 times.
3 times
Negative.
minus 483, 3.6 kilojoules, all right? Okay, so again, we add these up, and when you add these up, you should get this equation here, right? So let's see. What will cancel out? Let's see. These 6 hydrogens will cancel out with these 6 hydrogens. These 2 nitrogens will cancel out with those 2 nitrogens. And I think that's all as far as canceling is concerned. So we'll just write on what is left, which would be 4 ammonia plus 5 O2 gas. And then and you understand how we get 5, right? We get 5 by adding 2 plus 3 here, right? And then on the right side, you're gonna end up with 4 NO gas plus 6 H2O gas. So that means that now we need to work out what delta H is by adding up all these. So let me work these out first. So 91.8 times 2. So according to my calculation, this will be 184 kilojoules. This here would be 180.5 times 2. So that's 361, and that should be minus, by the way. 361.0. Do this properly. Minus 361.0 kilojoules. And then now for 3 times 483.6. So according to my calculation, this works out to be equal to minus 1,451 kilojoules, all right? And then we add these up. So 184 minus 361 minus 1451. And according to my calculations, this works out to be equal to minus 1628 kilojoules. And that's how that is done. Yes, sir.
And how are you running it?
Oh, so basically, because these numbers are exact numbers, we only look at these to determine the extent to which you round off your hands. So like in this case here, this is 3 sig figs, so we round off to 3 sig figs. This is 4, that's 4, that's 4, that's 4. All right, and then when you add them up, you round off to according to the lowest number of decimal places, which is 0. So therefore, yes, ma'am. Because in the case of the last two, you have, in the case of the NO here, it's on the right. It's on the right here. Right? And in the case of the H2O here, they're both on the right as well. So you leave those as is, but you have to multiply by, in this case, because there were 4 here, you have to multiply this by 2. Well, the entire equation by 2. And in this case here, because you have 6 here, you have to multiply this entire equation by 3. Exactly. Right. You have to flip the NH3 here because it's on the left in this equation. All right. Okay. Any other questions about this? Any other questions?
So when
Okay.
you have to flip the
I'm sorry?
things, when you have to flip the equation, for the delta H, it switches signs.
Yes, exactly. Whenever you have to flip, if it's negative before, it's become positive and vice versa.
All right, thank you.
Okay, so is it okay for me to clear this? All right. And I think there are 2 more problems of this type in the assignment. Let me just check down here. Okay, so let me hear what you have to say about this one. With minimal help from yours truly. This is the equation that you're trying to find delta H on, right here. And they gave you these 3 equations. Exactly, you don't have to do anything to this one. I'm just gonna rewrite it down here. C2H4. And the reason why, just in case you don't get it, or you don't catch it, the C2H4 is on the right side here, and it's only one of them, so that means I will just write this down unchanged. 2 CO2 gas plus 2 H2O liquid. And delta H for that remains unchanged as well, minus 1411 kilojoules. Okay, what else?
Second.
Okay, very good, because you have the C2H6 on the right side here, it's on the left side here. So I would flip it to get 2 CO2 gas plus 3 H2O liquid. And then on the right side, you're gonna have C2H6 gas plus 7/2 O2 gas. And what happens to the delta H?
Change signs.
1560 kilojoules. Okay, very good. What next?
Or would you have to switch the H2 to the right side?
Okay, why? Because you have. No, actually,
Maybe
you don't
no,
switch
no,
it.
I thought the error was before, I'm sorry.
No, actually, you don't switch it because the H2 is on the right side, on the left side here, left side here. So I'll just rewrite this down here. H2 gas plus half O2 gas to give H2O liquid. So therefore, the delta H for that one remains the same, which is minus 285.8 kilojoules, all right? And then, of course, as we did before, we add them up. So what will cancel out? Those, okay, those three will cancel out these two and that one on the right side. Anything else? It's CO2s, okay. Anything else? The O2, because you have 3.5 here on this side, which cancels out with 7/2 on this side, which is 3.5. So you're left with C2H4 gas plus H2 gas to give C2H6 gas. And the delta H for that would be the sum of these. So that's 1411 minus plus 1560 minus 285.8. And according to my calculations, this needs to be rounded up to 0.6 decimal places. So according to my calculations, 1 minus 137 kilojoules will be the final answer. All right. Okay, any questions about this one? Any questions? Any questions? All right. I can clear this, right? Okay, another one. Okay, so again, they gave you the equation, which is this here, to find delta H. And you're going to, I'm sorry?
You divide, we switch it, or is it all multiplying?
I'm sorry.
Like, you know how we've been multiplying, when it's a bigger number, could we divide, switch 2 to the first?
Oh, yeah, or multiply by a fraction, same thing, yeah. Okay, so let me hear what you have to say about doing this problem. Let's start off with this equation here. What would you do to this equation here, based on the first equation?
Switch the NH.
Switch the equation, switch your equation and
Multiply by half. Or divide by 2.
or divide by 2. Okay, so basically you're going to switch and divide by 2, so the equation becomes NH3 gas to form half N2 gas plus 3/2 H2 gas Which means what happens to delta H in this case?
Sign divided by two.
I'm sorry?
Flip the sign.
Change the sign and divide by 2 or multiply by half. So that's half of 91.8 kilojoules. All right? What about this equation? What would you do to this equation?
That's what-
Hmm? Correct, so CH4 gas to give C solid plus 2H2 gas, and delta H becomes what? Positive 74.9 kilojoules, all right? And then the last equation, what would you do to that equation? Multiply right through by 2, so you're gonna end up with 2H2 gas plus 2 carbon solid plus 2 N2 gas to give 4 HCN, and delta H for that would be equal to 2 times 270.3 kilojoules. All right, so when we add these up, what will cancel out?
Two H2s.
Okay, the H2s. Hold on, wait a minute. Oh, yeah. The H2s will cancel out here and here. There's something looks weird. Hold on, 1 minute.
I think we're supposed to divide by two on the third one, not multiply, because there's 2 in the delta.
Right, I knew something was wrong. Right, you're absolutely right.
If we do that, then the nitrogen is cancel out.
Hold on. We're supposed to divide by 2. Yeah, thank you. So in this case here, let me just write down the equation resulting from divided by 2. So going down here, we're doing, or I prefer to say multiply by half, right? So when you do that, you're going to get half H2 gas plus C solid plus half N2 gas, and then HCl, right? And delta H for that would be equal to what? Half of 270.3, all right? Kilojoules. Okay, so the H2s will cancel out still, because what happens is that these 2 H2s will cancel out. Oh, wait a minute. Something is still wrong. Something is still wrong. Let me rewrite this here. This should be page.
If you cancel out the half the.
Oh, right, okay, right, so these here, right, that's 2.5 H2 that we cancel out with, no, there's something still up.
Give a 3. The half plus the 3 halves give you 2, which you cancel out. Should be 1. Then you have 3 H2.
The half plus the
3 halves, right?
yeah, but that was still, oh, okay, all right, yeah, you're right. So, let me just correct this here again. So this would be plus 3/2 H2, and this would be plus 2 H2, gas. So this half will cancel out, 1 half you're leaving behind 1, right? So you're gonna end up with 3 H2s in there. Okay, so this will be canceled, leaving behind 1 right here. The carbons will cancel out here and here. The nitrogens will cancel out here and here. And what are you left with? You're left with, when you add them up, NH3 gas plus CH4 gas to give a total of, well, you're gonna get ACN over here. And then this plus that gives you 3H2. Right? ACN gas, gas. So basically, we add up all of this here to get your final delta H. So what I'm gonna do here is work out what 91.8 times 2 gives. So that gives 184 kilojoules. And then this here, 0.5 times 270, oops, do this again. 0.5 times 270.3. And this gives 132, I'm sorry, 135.2 kilojoules. And then we add them up, so 184 plus 74.9 plus 135.2. So according to my calculation, this gives me 394 kilojoules, right? Let me just do this again, just to be sure. 91.8 times 2, okay.
It's kind of 1.8
Here.
divided by 2.
On the first one. The 91 point,
Oh, okay, 0.5 times 91.8. So this should be 45.9, okay, thank you. Kilojoules. And then this one looks correct, so it's 45.9 plus 74.9 plus 135.2. So 256 is actually the answer, 256 kilojoules. All right, so that's basically how that is done. Okay, any questions about it? Any questions?
I thought you were supposed to round to the lowest decimal.
I'm sorry?
Are we supposed to round to the lowest decimal or just the number?
Well, when you're adding, you round off to the lowest number of decimal places. So since we have, oh, that's what I say, so this should be. So this should be 256.0. So it should be one decimal place. Thank you very much. All right, any other questions? Any other questions? 256.0? Okay, so there's one more, if we're finished with this, there's one more topic that we need to cover in order to end this chapter. Let me do this. And that has to do with the concept of standard enthalpy of formation. All right, so let's talk about that. So basically, first thing we're going to talk about is the whole concept of enthalpy, right? Now, by definition, the change in enthalpy of a reaction would be the final value for the enthalpy minus the initial value of the enthalpy, right? That would be how you calculate that if you have those two values. Unfortunately, it is not possible to determine the enthalpy of anything by itself, of any substance, right? So basically, what we have to do is, since we cannot obtain the absolute values, we have to use a relative scale in order to determine, at least on paper when you're doing your calculations, the change in enthalpy of a reaction. So what we need to do in order to establish a relative scale is to define what is called a standard state of a substance, right? And the conditions related to the standard state. And the conditions that have been adopted by the powers that be, it says that basically the standard state would be 1 atmosphere pressure for any gases involved, and the temperature would be 25 degrees Celsius. And there's another condition too. Let's see if I can write it down here. Oh, I can't, at least not here. Another condition would be that for solutions, molarity would have to be equal to 1.0 m, right? So those are the standard conditions that is used to establish the relative scale. All right. So this brings us to defining what is known as the standard enthalpy change of reaction, which is an enthalpy change of reaction under those conditions that I mentioned, right? where the reactants and products are in their standard states. 1 atmosphere pressure for gases, 1 molar solutions, and temperature is equal to 25 degrees Celsius. And by the way, please do not confuse this standard state with STP that we were discussing when we were talking about gases, right? STP, well, not totally different, but different, because STP stands for standard temperature pressure, where the pressure is indeed 1 atmosphere, just like this, but the temperature would be 0 degrees Celsius, all right, or 273 Kelvin, all right? But so this is different from STP, all right? Now that's a standard enthalpy change for reaction. Now there's another definition that you need to be aware of, and that is the standard enthalpy of formation for a substance. And here's the definition. It is the enthalpy change that occurs when 1 mole of a substance is formed from its elements in their standard states, all right? So that's the enthalpy of formation. So please note the difference in the designation between these two. This is delta H with a small o right there. That small o represents standard conditions, right? Whenever you see that. And this is not only true for enthalpy, but for some other things that you're going to learn. For those of you who have to do Chem 2, you're going to learn about some other values where they use the symbol right here. Whenever you see that symbol, it means the standard conditions apply, right? And in this case here, you have delta HF standard. F means formation, meaning formation of 1 mole of the particular substance from their constituent elements under standard conditions, all right? So that's important, and that establishes the relative scale, which you can use to calculate the delta H of a reaction. If you have these values here, you can calculate the delta H under standard conditions for pretty much any reaction, but of course you have to be given the values, and there are actually values that are given in a table. I'm going to show you shortly where those values are. Get rid of this here. Okay, so just to give an example, let's say you want to determine the enthalpy of formation of liquid methanol, right? So you'll notice that methanol is made up of 3 elements, carbon, hydrogen, and oxygen, right? So what you do in order to write down the equation for the formation of 1 mole of methanol is that you start off with the elements on this side here, right? Carbon, hydrogen, and oxygen, and then you draw an arrow, and then you write down methanol here, and then you keep this number here fixed as 1. The coefficient for the methanol is fixed at 1, and you balance the rest of the equation based on that, right? So that's why you notice that there's a half O2 here, because there's 1 O on this side. So in order to make sure that the oxygens are balanced, you have half O2, that is 1, that is 1. You still have a coefficient of 1 here, and you balance the other elements as well. And it turns out that for this equation here, the enthalpy of formation of methanol is minus 238.7 kilojoules, right? So those are that's basically how you get the enthalpy of formation. And we use those relative values as if they're absolute values when it comes to determining the enthalpy changes for any chemical reactions involving these substances. So let's see here. Oops, sorry. Now here's a very interesting question. Based on a definition. So here's the definition, as I said before. The enthalpy of formation of a substance is the enthalpy for the formation of 1 mole of the substance from its elements under standard condition, right? So this question is asking, what is the enthalpy of formation standard for an element? Any element, carbon, oxygen, nitrogen, right? And here's a hint. The reactants are the same as the products. In other words, let's say it's oxygen we're dealing with. Okay, that. Oh shoot, sorry. Sorry folks, for those of you out there in Zoom. Okay, so let's say the element is oxygen. What's the enthalpy change for the formation of oxygen from oxygen?
There is no change.
0, exactly, right? So therefore, this is true for all elements, right? As long as the elements exist as by itself under standard conditions, the enthalpy of formation of those elements from their elements is equal to 0, right? Okay, so let me see what else. So basically, before I do that, let me show you the table that you're gonna use to do these types of calculations. So let me go to files. We close this. Let me go to tables. And okay, so this is the table that you'll have access to. And for all purposes, we'll be concerned with only this column right here, right? Now, for those of you who have to do Chem 2, you'll be using these two when you get to that level. But for all purposes, we're just concerned with the enthalpy of formation column right here, all right? So basically, these are the values that you're going to use for these different substances. And you'll notice what we just said. For elements by themselves, not combined with anything under standard conditions, their values are always 0 here. That's for aluminum, that's for arsenic, that's for barium, that's for boron, all elements by themselves, bromine in a liquid state, calcium and so on, all elements by themselves, not combined with anything, their enthalpy values will be equal to 0. So these are the values that you'll be using in the calculation of the type that we're going to talk about shortly. Okay, so let me clear this first. And then go back to the PowerPoint. Okay, so basically, how do we use these values to calculate the enthalpy change of a reaction? Well, basically, it comes down to this equation right here. And let me explain what this equation is saying. This equation is saying that the enthalpy of the reaction will be equal to the sum of the enthalpy of the products minus the sum of the enthalpy of the reactants. All right. Now, I don't know if you're familiar with this symbol, this Greek symbol. That's capital sigma, right? And in math, I remember way back when I did statistics and so on in undergrad, this is representing sum of, right? So you should read this as sum of the enthalpy of the products and minus the sum of the enthalpy of the reactants, right? Now, this other Greek symbol called nu represents the coefficients, right? So what you need to do in order to do this type of calculation is that for each enthalpy value of each substance, you're going to multiply that value by the coefficients of that substance that you'll obtain from the balance equation, all right? So you have to take that into account as well. The stoichiometry is important when it comes to determining ultimately the enthalpy change of the reaction. And I think I may have an example, two examples, okay. So let me, again, I'm gonna need some space. So let me do this one here. I'm gonna do the first one and I'm gonna leave the second one for you to do on your own. And so the question gives you, oh shoot, you know something, I'm gonna need a table. Okay, so the question gives you this equation here, and it's asking for you to find the delta H of this equation using the table, the values in the table here. So let me see here. Let me go here. Well, before I even get to the table, let me go back. Okay, so the first thing I will do is write down the equation for calculating the delta H value. So what I would start off by doing is saying delta H standard for the reaction is equal to, so remember now, it's the products, the sum of the enthalpy of the products minus the sum of the enthalpy of the reactant, right? So these are the products, of course, obviously over here on the right side. So I'll start off with the carbon monoxide, but because there's a 4 here, I'm going to write down 4 times the enthalpy of formation of carbon monoxide plus the enthalpy of formation of hydrogen. Now, hydrogen is an element by itself, not combined with anything. So as I said before, that value is 0, right? So that takes care of that. And then I would subtract from that the sum of the coefficients of the sum of the enthalpies of the reactant. So the first reactant here is CH4 multiplied by 3. So 3 times the enthalpy of formation of CH4 plus 2 times the enthalpy of formation of H2O plus the enthalpy of formation of carbon dioxide. All right. And that's the setup. So all we have to do now is consult the tables. So I have to minimize this a bit. So in the case of carbon monoxide, so here's a table, carbon monoxide, and these are, if I'm not mistaken, arranged in alphabetical order, so that should make it a bit easier, I think. I hope. Carbon dioxide. Okay, so for carbon dioxide, the value is minus 393.51. So I'm going to have here 4 times 393.51 kilojoules. All right, so that takes care of that. Because this is 0, so I don't need to do anything else as far as the products are concerned. And then minus for the reactants, 3 times the enthalpy change of CH4. Now, let me just say this, in this particular table here, they have a separate listing for organic molecules at the end, and CH4, of course, is an organic substance. So this is it right here. And the enthalpy of formation of CH4 is minus 74.81. So, minus 74.81 kilojoules plus, and then for water, I need to go back up. Water. H. Okay, and you have to pay attention to the states, right? The question says that water is in a liquid state. So that will be this value right here, which would be minus 285.83. So that will be 2 times minus 285.83 kilojoules. And then the last one is carbon dioxide. So you have to scroll up. Carbon dioxide, where's carbon dioxide? And I think, hold on. Carbon dioxide is minus 393. I think I may have made a mistake. Let's check something here. Yes, I made a mistake. This should be for carbon monoxide. So let me erase this here. So for carbon monoxide, that should be minus 110.53. All right. Okay, so that's basically what we get when we plug in the values into that equation. And therefore, all we have to do from here is the number crunching. So let's see here. So let's work out what's within the parentheses first. So for this one here, it is 110.53 times 4. So that gives you minus 442.12. All right, so kilojoules, of course. And then for this year, minus 74.81 times 3. So according to my calculation, this gives minus 224.4 kilojoules. Plus, and then for the next one, it's minus 285.83 times 2. So this gives you minus 571.66 kilojoules. And then to that, I will add minus 393.51 kilojoules. All right. So let's do this now. So do this here. So 442.12 minus, and then minus 4.4 minus 571.66 minus. Okay, so according to my calculations, let's see to what extent we need to round this out to 1 decimal place. So the answer I got here is 747.5 kilojoules. And that's what I got. All right. So that's basically how you calculate the enthalpy change of any reaction. Of course, you have to consult the table and look up the values. And as you can see, that takes basically most of the time in terms of solving the problem. Once you get those numbers, you plug them into the equation, and then that's it. You get your delta H value. All right.
How did you get the coefficient for the first bracket?
Because in the balanced equation, that's what the carbon
I
monoxide
didn't
is.
see it. So I was just.
Oh, right, yeah.
Thank you.
Right, you multiply each of their respective enthalpy of formation values by their respective coefficients, right?
Or do you do the CO plus O? On that
Yeah.
first one,
Right, because hydrogen is value 0. Remember, elements by themselves, uncombined with anything, 0, right?
Gotcha.
So therefore, you don't even need to look at it because we're gonna see it in the table anyway, right?
thank you.
Okay, any other questions about this one? Any other questions? Any other questions? All right, so going back to the assignment. Now, I don't know if I told you this, but there are 2 files for assignment number 6. So you need to see if I can bring this up. Right, where it says assignment number 6 addendum. You need to do that one and attach it to
Is it just a one extra page?
yeah, basically just one extra page, yeah.
Is there a due date yet for that?
I'm going to do that, establish that before you leave here today.
I think it's already on. Because I have it on mine. I can't.
Oh, it is?
Yeah.
Oh, okay. I guess I forgot I corrected that. Okay. So basically, these questions are on the same time, right? Basically, you're asked to determine the delta H of these reactions. So again, you have to search for those values in the table. Some of the product values, some of the reactant values, and products minus reactants, and that's it. So that's basically what is involved in each of these here. All right. So make sure you use the values from the tables in order to do these questions. So, okay, so let me go here and set up the assignment due date. Okay, so this is assignment number 6. And okay, so I would say next Tuesday. Right? Let me see here, so available from today. Okay, and it's not public, so. Now you can submit that, all right. So that's pretty much it for this chapter, so next time we meet, we're gonna start with chapter 7. Which deals with, if I remember correctly, atomic structure, so something for you to look for.
We got number 6 here,
Oh, okay.
with this being 5 grand, do you have to, figure out the whole per grand?
No. Basically, what the question is asking for is the final temperature of sample B, right? So what I would do is, what I would do is. Okay. Okay. And temperature rise, okay. And then, oh, okay, so basically. The equation you're using is Q is equal to M times C times delta T, right? Now, they're both cobalt, both samples are cobalt, which means that C will be the same.
Okay.
You see what I'm saying? So what I would do is find out what C is based on the first information given. So C, of course, be equal to Q divided by M times delta T, right? So Q is 6.70 joules. M is 5.00 grams, and the change in temperature would be the difference between the 27.9, so 2.9 degrees Celsius, right? So that will give you the specific heat. 6.7 divided by 5 divided by 2.9. So that gives you 0.462. And this will be joules per gram degree Celsius, right? Now, in the case of sample B, they gave you the heat. They gave you the mass and the initial temperature. They're asking for the final temperature. So you're still using this equation, but this time you're trying to find delta T. So delta T would be equal to Q over M times C. So Q in this case is 5.00 joules divided by M, which is 7.00 grams, times C, which is the same as. So this will be delta T, and once you find delta T, of course, will be equal to final temperature minus the initial temperature, right? What the question is asking for is the final temperature, so T2 will be equal to delta T plus T1, right? So delta T would be whatever you have here, right? And T1 would be the initial, exactly. Would be, so this would be delta T plus 25 degrees Celsius. Whatever that gives, that would be the answer.
Awesome. Thank you, sir.
Yes, sir.
So I just had a question
Mhm.
about the last problem we did.
Mhm.
So I put in all the values, but I was curious as to how you got to that answer, because we're adding negative values here. Like all these values are negative. So
You're minusing a negative, so you add a
well,
positive.
but only for the first one though, and then you're adding negatives to the next.
Oh, so the sign might be off, that's what you're saying? Because,
Well, I mean, look, so for the first one.
well, all of these are negative, right? And you have a negative sign here, so that becomes positive. And, if I remember correctly, this was positive, right? Or was it?
Yeah, that one's fine.
Yeah, so basically, the result should be positive, because if all these are negative, and they have a negative sign in front of all of these, when you add them up, whoops, sorry. When you add them up and put a negative sign in front, then that will be positive, and then you're adding that to a positive number.
Okay, I guess I just looked at it.
Right,
Right.
Right, so the answer should be positive.
The initial, the 442 is negative.
Oh, it is?
Yes.
Oh, in that case, that might change things a bit.
That was.
I think that comes from the
Oh,
table.
because it's negative 4 times. I didn't see it was negative.
Okay, all right, so,
I thought, it was okay, that
Right.
makes sense.
okay, so yeah, I need to tell the class that. Thank you for, so this should be, so I don't know, I'd have to rework this again and see what the answer is.
Well, I mean, it's not, if it's, I mean, if it was negative.
So, right, okay, yeah, I'll do that. Oh, yes, sir.
It was about 12:30 when I finished. the sheet. So,
Mhm.
and instead of emailing, I figured I'd just bring it in,
Okay,
so, okay.
all right, yeah, and this is what assignment for?
And then I saw online that you said
Mhm.
paper submission only. So we're like done on paper only, so I was just. I didn't know if you wanted us to turn it online. That's,
Well, I'll take it, I mean, I was expecting it online, but,
oh, okay. Sorry, I saw like in the special instructions or something like that, there was. it's-
no, I think what I meant to say, I don't know if I said it clearly, but what I meant to say was that I wanted it done on the original document, because some people were turning in assignments on, you know, like blank piece of paper and so on, so.
Which
Oh,
one,
okay.
which one was that for?
Oh, the test.
That's two.
Test number 2. But I'll take it, I mean, you know,
But I really appreciate it too.
Also, can I take the chapter 4?
Okay. no problem.
Thank you, sir. I appreciate it.
Okay, let's see,
Supposed to be pretty hot next week.
well, I ain't complaining.
Gonna try to get on the boat this weekend.
Yeah, right? I know, I went,
Okay, let me see.
what, last week,
Uh,
they're just like, are you just like going out of the boat, be on the boat, or like fishing?
No, just go ride. My wife's gonna be out of town this weekend, so
Oh,
I
yeah.
got a 6-year-old and a 2-year-old, so
Yeah.
just go for a boat ride and go to the springs, go swimming.
Hope nothing goes wrong.
Okay, those of you out there in Zoom, I'll be signing off right now.